Last time we were talking about concentration units. So in chapter 4 we learned molarity, moles per liter, and then last time we learned about molality with an L, which is moles per kilogram of just the solvent. And this was the problem that we did last time. Given this information, determine the concentration units in molality, parts per million, and percent by mass. We went ahead and did the molality. We haven't done the percent by mass or parts per million yet. So this time, let's go ahead and do those second two, the percent by mass and parts per million. So percent by mass, any sort of percent by mass is going to be the mass of your solute, whatever is getting dissolved, divided by your mass of solute plus solvent, or the total solution, then times 100. And that's where the percent, meaning per 100, comes from. So this is percent. If you want this to be parts per million, instead of multiplying by 100, you're going to multiply by what? A million, right? 1 followed by 6 zeros. And that would make this parts per million. But this part of the equation is the same. So let's do those two for this problem. So 170.1 grams of glucose. That is our mass of what? Solute, solvent, solution? Glucose. Is that our solute or solvent? Glucose, the sugar. Solute, that's what's getting dissolved. So that's what goes in the top of the equation. So mass of solute for this is going to be 170.1. The bottom of the equation is the mass of the solute plus solvent, or the solution. Was I given the mass of the solution? Do I know how many grams of solution do I have? No, but do I have information I can use to find grams of solution? Yes, I'm given volume, a liter, and I'm given density. So if we take our density equation, density is mass over volume, rearrange it. Density times volume will give us the mass of the solution. So if we go ahead and plug those in, so the density of the solution, mass, I'll put solution, is the density 1.062 grams per milliliter times the volume. Now we're told it's a liter, so how many milliliters is that? How many milliliters in a liter? 1,000. You know this. 1,000. All right, 1,000 milliliters. So milliliters cancel. We're left with grams. 1,062 grams of solution. So to find percent by mass, we're going to take those grams of glucose, 170.1, divided by the grams of solution, 1,062 grams of solution, and then times it by 1,000, or 100, to make it a percentage. So what is this percent by solution? 16.02. Now to make this parts per million, what's the only thing different we're going to do? Good. So to multiply by 100, we're going to multiply by a million. So that's a big number. We'll just do that in scientific notation because 0.602 times 10 to the what? Yes?
When you have to subtract your mass of glucose from your mass of your solution.
So we did that last time because in molality you only need kilograms of the solvent. So that's what we did last time because we just wanted the water, so we subtracted off the mass of the glucose. Here in the bottom of the equation, it's the solute plus the solvent. So that's why we didn't subtract off the glucose this time. But in molality, it's just the solvent. So this is 10 to the 5th per million. How we feel about those three new concentration units: molality, percent by mass, and parts per million.
So how can you tell which one is the solute and solvent again?
The solute's always in larger, or solute is always in smaller proportion. The solvent's always in larger proportion. And then with aqueous solutions, usually the solute is whatever's just the solid being dissolved in water. All right. So, why would you use one concentration over the other? What are the advantages of the other? So in Chapter 4, we only dealt with molarity because that's the most common unit that we use here in a chemistry lab. Now, there are some disadvantages. It's a little bit trickier to determine molarity when you're making a solution because you can't just add a mass of solid to a specific volume of water and say, okay, here's the molarity, because the resulting volume is going to change. Even if you're dissolving a solid into a liquid, such as sugar into water, it's still going to cause a change in volume. So it's a little bit trickier. In those cases, molality is a little bit easier to calculate. Also, molality is independent of the temperature. What this means is that as you change the temperature, you're going to change the density. Changing the density changes the volume. Changing the volume changes the molarity without ever actually changing the amount of solute to solvent proportion. It just changes the volume, which changes the molarity. Whereas molality, because it goes by mass, mass is independent of temperature, so it's not going to change. Percent by mass is also independent of temperature, so we also, for percent by mass, don't need to know the molar mass of the solute. This is useful if you're making a solution of something that you may not know what the molar mass of the solute is. Say you're making a concentration of a protein. Proteins are very, very big. These things have huge molar masses that are sometimes very difficult to calculate. You can find the percent by mass of it just by measuring the mass of each component that went into the solution. But it's a lot harder to find molarity and molality if you don't know what the molar mass of the substance is. So that's another advantage of percent by mass. We already talked about things like parts per million and parts per thousand being useful when you're measuring something that's a very low concentration, such as the amount of mercury found in seawater, hopefully a small number, or the amount of lead in your blood, again, hopefully a small number. So rather than saying 0.0000001%, it's easier to say 0.1 parts per million or something like that. So let's compare going from one concentration unit to another. So in this problem, we're given the concentration in percent by mass, and we want to take this percent by mass and convert it to both molarity and molality. So the information given is that it is 70% by mass, and this is isopropyl alcohol, 70% by mass. So what's the other 30%? Water, yep. And that it has a density of 0.79 grams per milliliter at 20 degrees Celsius. So we're asked to express this in units of molarity and molality. Molarity and molality. So remember, molarity is moles of solute divided by liters of solution, and that is big M. While molality, that's a lowercase, kind of curvy m. Molality is still moles of solute on the top, but on the bottom it's now kilograms of just the solvent. And the other thing we're given is the molar mass of isopropyl alcohol is 60.09 grams per mole. So that will be useful in converting from its mass to its number of moles. So one thing we're not told here is we're not told what our starting amount of material is. concentration. Let's go way back to chapter 1. Intensive properties versus extensive properties. Intensive properties do not depend on the amount of matter. Extensive properties do depend on the amount of matter. So extensive properties are things like its mass and its volume will change as you change the amount of material, whereas intensive properties are things like its boiling point or its density do not change as you change the amount of material. Concentration is also going to be intensive in the idea that if I have a cup of water that is 70% isopropyl alcohol, 30% water, and I pour half out, it's still 70% isopropyl alcohol, which means we can choose any sample size that we want to. So we're going to choose a sample size that's going to make our math as easy as possible. So if we're dealing with percent by mass here, or if we're dealing with kilograms of solvent, we're going to pick something that's going to be whatever would go on the bottom as a whole number. So let's see. Let's pick grams of solution. What do they do? We can really pick any number we want to here. 1 liter, sure. We'll do 1 liter of solution. Let me get a blank slide. All right. So step 1, choose whatever starting material or what amount of starting material you want. So let's just choose 1 liter of solution. So assume 1 liter. So first of all, we're going to take that liter and use this density to convert that liter into a mass. So 0.79 grams per milliliter. Again, density is mass over volume. So mass is density times volume. So our mass of solution, now this is where it becomes important to specify which mass you're talking about. Are we talking about the mass of the solution, mass of the solvent, mass of the solute? Right now we're talking about for the full solution. It's going to be that density, 0.79 grams per milliliter, times the volume. We assumed 1 liter, so 1,000 milliliters. So 790 grams of solution. Now, of those 790 grams of solution, what percentage is the isopropyl alcohol? 70%. So if you want to know what a percentage of something is, how do you do that math? If I'm a salesperson and I've sold $100 worth of shoes and I get 20% commission, that sounds great. How do I figure out what my commission is? Times it by 20 or 0.20. So we're going to take this 790 grams of solution and multiply it by what? 0.7. Good. 0.7, and that will give us grams of what? The isopropyl alcohol, which is our solute. So what number does that give us? Good. 553. 553 grams of solute. So we now have our grams of isopropyl alcohol. So now that I have my grams of isopropyl alcohol, looking at both of our concentration units, what do I want those in? Not grams, but what? Moles. In both cases, I need that isopropyl alcohol in moles. So how am I going to get to moles if I've got grams? Multiply by it or divide by it? Divide by it. Divide by the molar mass. So moles are the grams divided by molar mass. Back to chapter 3. So 553 grams divided by that molar mass of 60.09 grams per mole. And this is why we divide, because now what happens to our units? We're left with moles. Good. Grams will cancel. We'll be left with moles of isopropyl alcohol, which is our solute. How many moles do we have? Yeah, 9.2 moles of solute. And our two concentration units, molarity and molality. Which one looks easier to calculate right now, molarity or molality? Molarity, because we have moles, 9.20 moles, and liters. How many liters do we have? 1. Good, we start with 1 liter. So what's our molarity? 9.2, good. I think we only had 2 sig figs in our density, so we'll use 2 significant figures. So there's our molarity. Now molality. Mole still goes on top, so that 9.2 still goes on the top, but on the bottom is kilograms of solvent. All right, so think about how can we figure out kilograms of solvent? Good, subtract 553, which is our solute, from 790, which is our total solution. So 790 grams with a solution, minus 553 grams was the solute. What is left over should just be the solvent. Yep, 237. So do we put 237 on the bottom? What unit is 237 in? Grams. What unit do we need it in? Kilograms. Good. So what is that in kilograms? Good. And on the bottom, or on the top, is still the moles. So the molarity was 9.2. What's the molality? 38.8. We've got 2 sig figs, so we'll just round that to 39. Molality. The higher your concentration, the more these two numbers are going to vary. At low concentrations, molarity and molality are very similar numbers. But at very high concentrations, and 70% is pretty high, then these numbers are going to vary more greatly, because the higher the concentration, the more that's going to change that density. How do we feel about concentration units? Be able to calculate it and be able to do this, convert from one concentration unit to the other, given the information. Can do that? All right. So next we're going on to factors that affect solubility. So these are what, the solubility again is how much can dissolve in solution. So there's 2 primary things that can affect how much can dissolve in solution. We've already briefly talked about how temperature can affect the solubility when we talked about how do you make a supersaturated solution of sugar water when you're making your sweet tea. How did you do that? How do we make supersaturated sugar water for our sweet tea?
Put it while it's hot.
You increase the temperature, right? You make it hot. Increasing the temperature, increase the solubility. The other thing we talked about very briefly, but didn't talk about specifically, is pressure. So carbon dioxide dissolved in water. What is a consumer product that has carbon dioxide dissolved in water? Soda, right? So when you open that soda bottle, if you leave it open, release the pressure, what happens to the carbon dioxide that's dissolved in it? Does it all stay dissolved? It escapes. So the solubility goes down when you release that pressure. And if you leave that bottle open and leave the pressure, open, so it's not increasing the pressure, over time, what happens to how much carbon dioxide is dissolved in there? You come back after leaving your Coke bottle open all day, is it still bubbly? No, it's gone flat. What does it mean by gone flat? No more carbon dioxide. All the carbon dioxide, well, not all of it, but a large portion of it has escaped the solution. So pressure is going to be another thing that's going to affect solubility. So we're going to talk about how these two can affect it. So this image, figure 13.4, is on page 573, and it shows how most compounds, as they dissolve in water, now this is their solubility and how many grams of it will dissolve in 100 milliliters of water. For most substances here, you can see they increase as you increase temperature. So right here, there's sugar, glucose. That's a sharp increase. You increase this temperature, it starts increasing very rapidly how much can dissolve in water. Here's sodium acetate. This is the solution that I showed you last time that was supersaturated. I added the crystal and it recrystallized. That's sodium acetate there. So what about here, sodium chloride, table salt? As we increase the temperature, what happens to its solubility? Flat. What does that mean? It's not affected. It's not affected. So last year when you guys were doing the separation of a mixture lab and you had to separate out the salt from the sand, and a lot of your procedures, and I didn't take it off, some of them I did make a comment, a lot of you guys said increase the temperature to increase the solubility of the salt. And I didn't really make a comment because we hadn't talked about it, but actually increasing the temperature does not increase the solubility of the salt. It may increase how quickly it dissolves, but it does not ultimately increase how much sodium chloride will dissolve in that water. Now here we have, at the very bottom here, that's cesium sulfate there. It actually decreases a little bit as you increase the temperature. So we're not going to talk too much about calculations for this. Just be aware of being able to look at a graph like this and be able to tell me, for the substance I've given you a graph for, is the solubility going to increase, decrease, or stay stagnant as you increase the temperature, just by looking at the curve. All right, so now let's talk about that pressure. So this is the soda bottle. Pressure versus solubility can be calculated using an equation called Henry's law. So this equation is on page 574, equation 13.3, and it says C, the concentration, is proportional to the pressure using a proportionality constant K, which is the Henry's law constant. So C here is in moles per liter, also known as molarity. P is the pressure in atmospheres, and then K is your Henry's law constant. So according to this, as you increase the pressure, what happens to the concentration of a substance? If I increase P, the pressure, what happens to C, my concentration? It goes up. Good. Now, what state of matter is most affected by pressure? Solid, liquid, or gas? Gas. So we're typically dealing with Henry's law, we're dealing with a gas being dissolved in a liquid, such as carbon dioxide bubbles being dissolved in water to make soda here. Now, as for that Henry's law constant, it is different for every substance at every temperature, because this is also still affected by temperature. You would either have to be given that or be given enough information to calculate what that Henry's law constant is. But again, the equation is just C is equal to Kp. All right. So this is just showing you a schematic of, As you increase the pressure, more of these gas particles are going to end up being dissolved in the solution to escape from the gas phase. Because as you increase the pressure, those things are going to bounce off the walls more, collide with each other more, and by going into the solution, they avoid that whole collision process. Let's try this out. So this example 13.4 on page 575, calculate the concentration of carbon dioxide in a soft drink that was bottled under a partial pressure of 5 atmospheres of carbon dioxide at 25 degrees Celsius before it's opened, and then after it has gone flat at 25 degrees Celsius. So I guess we're going to assume that's 1 atmosphere. It's gone flat. Oh no, we're told. We're not told there. The partial pressure of carbon dioxide in air is 0.0003 atmospheres. So that's where it's flat. 0.0003 atmospheres. Because partial pressures, we only worry about the pressure of that specific gas. Majority of the 1 atmosphere of pressure we feel is not carbon dioxide, it's what? In this room right now, when we feel 1 atmosphere of pressure on us, that's not mostly carbon dioxide, it's mostly what gas is putting that pressure on us? Nitrogen is mostly the nitrogen. So we're only worried because gases don't care about the other gases in the room, they only care about the same gas. So we're only going to worry about the partial pressure of just the carbon dioxide at that 0.0003 atmospheres. All right, so the Henry's law constant for carbon dioxide in water at this room temperature is 3.10 times 10 to the negative 2 moles per liter times atmospheres. So first we're going to calculate what the concentration is at 5 atmospheres before it's opened. So again, our equation is concentration is equal to the Henry's law constant times the pressure. So here, Henry's law constant, 3.1 times 10 to the negative 2 moles per liter atmospheres, times before it's opened, what is its pressure, P? 5 atmospheres. So atmospheres will cancel, and we'll just be left with moles per liter, which is molarity. And we were only given 2 significant figures. What's our molarity in 2 significant figures? 0.16, good. 0.16 molar. So that's what it was when it was bottled at 5 atmospheres. So go ahead and try finding what it would be after it's gone flat, where the partial pressure is 0.003 atmospheres. Good. 9 to the 10 times 10 to the negative 6. Molar. Now there's only 1 sig fig in this, so that's why I'm only using 1 sig fig here. Anybody not get that concentration? Good. How do we feel about Henry's law? Can we do that? It's like 12 of these ones on the test, and we'll be good to go. We won't overthink them. Don't overthink them. All right. So that's it for section 4. So next we have colligative properties. Colligative properties. So colligative properties are properties that depend on the concentration only, not on the identity of the solute. They only depend on the concentration. So we're going to talk about different colligative properties. Vapor pressure lowering. So how is the vapor pressure affected by the concentration? Boiling point and freezing point. So this is, why does grandma always add salt to the water before boiling for pasta? And why do we always add salt to the roads when we're trying to get them to stop freezing over? And then we'll talk about osmotic pressure. Why do we give a patient an IV of saline solution when they're dehydrated instead of just putting water into their veins? And electrolyte solutions, which we talked about briefly in chapter 4, but we're going to talk about them in a little bit more detail right now. So this week's lab is going to be a freezing point depression lab. So we're going to get to work on how the freezing point is affected directly using, we'll be using water and glycerol for this week's lab. So let's jump right in. Vapor pressure. So we talked about vapor pressure back in chapter 10. We were talking about it as the pressure that is over the surface of water, and you have to consider that when we were talking about gas mixtures. So we did a lab right at the end of the semester where we were collecting hydrogen gas over the water, and I had you guys subtract from it the partial pressure of the water from being collected over water. There's going to be some water vapor in in that case we were collecting with the udiometer. So here we go. The partial pressure of a non-volatile solute, meaning something that is not going to vaporize itself, dissolved into a vaporized or a volatile solvent, something that can vaporize, can be expressed using Raoult's law. Raoult's law says that the pressure, originally vapor pressure, is going, or sorry, the vapor pressure is equal to the mole fraction times the initial vapor pressure, or before you dissolved anything, what the vapor pressure was. So mole fraction was a unit that we used back in chapter 10, and it's just the fractional amount of the solute in moles divided by the solution in moles. So this is equation 13.4 on page 576. Raoult's law. So we can take this and kind of try and make an equation that's a little bit easier to use and come up with this last one here. This is equation 13.5, still on that page 573. That shows that the change in vapor pressure, or your vapor pressure lowering, how much it lowered by, is equal to x2, the mole fraction of the second component, or your non-volatile component, times the initial vapor pressure of your first component. That's going to be your volatile component. So if we're making salt water, your second component is the salt, so x2 would be the mole fraction of salt. And then water is your volatile component, so this would be the vapor pressure initially of water. Now the unit for the pressure doesn't matter as long as it's consistent. Whatever unit you're given will just be the unit you get out of the equation. You don't have to convert these back to atmospheres if you don't want to. I think this first sample problem, we're going to leave it in millimeters of mercury.
So what is all of that?
This is showing you how much it changes. If you're just asked what is the new vapor pressure, you can also use this equation. So this is your new vapor pressure. This is the initial vapor pressure, or the pressure of the pure solvent. X there. Vapor pressure of pure solvent. And this is the mole fraction, which in this case, x1 is the first component, or your volatile, or your solvent in this case. So if this is water that you're dealing with, this would be the mole fraction of water. So in this case, it would be moles of your solvent, divided by your total moles in your solution. And you don't multiply by 100. This is not a percentage. You just leave it as a fraction. And there's no units because moles cancel.
Is that solute or solvent, Tom?
Solvent, solvent, solvent. because 1 stands for the solvent, which is going to be your volatile component. For most of these, I'm going to give you, it's going to be water. It'll probably make more sense once you do an example. Just find the mole fraction multiplied by the vapor pressure of the pure solvent. That'll give you your new vapor pressure is. Are you try an example? Okay. Calculate the vapor pressure of water over a solution made by dissolving 225 grams of glucose in 575 grams of water at 35 degrees Celsius, given that at 35 degrees Celsius, the vapor pressure of pure water is 42.2 millimeters of mercury. So this is the equation we're going to use. What is our new vapor pressure? It's going to be equal to your mole fraction times the vapor pressure of the pure solvent. So this 42.2 millimeters of mercury, that's for pure water, so that is our P1. So all we need then is what is X1, the mole fraction of water. Mole fraction of water. So the mole fraction is just the moles of water divided by your total moles in this solution. Now, here's the problem. Was I given moles? No. Well, I was given what? Grams. Is that a problem? What? No, because what can we do? Convert those grams to moles. How do you convert grams to moles? Divide by the molar mass. And in the setup there, we've gone ahead and gotten the molar mass. If you didn't have that setup, you would just add off the periodic table carbon, hydrogen, oxygen for glucose, and then hydrogen and oxygen for water. So let's find first moles of glucose. Moles of glucose. So moles are equal to your grams divided by your molar mass. So we have 225 grams. Divided by molar mass of glucose is 180.2 grams per mole. So grams cancel. We're left with moles. 1.25 moles glucose. I do the same thing to find the moles of water. So now we have moles of both. Can we find the mole fraction? Yes. So mole fraction of water is going to be our moles of water, 31.9 moles of water, divided by the total moles. So we're going to take the moles of water again, and then we're going to add to that the moles that were glucose. Don't multiply by 100. Again, this is not a percentage. Leave it as a fraction, which means it should be less than 1. Now this colligative property is called vapor pressure lowering. So at the end, we expect our vapor pressure to be what compared to 42.2? Lower. Good. And make sure your answer is making sense here. So our mole fraction we got here to be 0.962. So that's what goes in here. So 0.962. So our new pressure is our mole fraction, 0.962. Times our initial vapor pressure, or vapor pressure of the pure substance, which was 42.2 millimeters of mercury. Now, because moles and mole fraction cancels, there is technically no unit for mole fraction, so our only unit here is millimeters of mercury. So what is going to be our final millimeters of mercury here for our new pressure? Good. 40.6. Millimeters of mercury. which is indeed lower than 42.2. So by adding sugar into the water, we lowered the vapor pressure. Now in chapter 10, when we were learning about these vapor pressures, in order for a solution to boil, its vapor pressure must reach what pressure? In order for a solution to boil. So at the boiling point, what happens to all of your liquid? It turns into what? Vapor. So if it's all vapor, that means that over top of the solution, the pressure of that vapor should be equal to the surrounding pressure. Now in chapter 10, when we were talking about this, we gave the example of if you lower the surrounding pressure, such as climbing up to the top of Mount Everest, where the pressure is very, very low, what happens to your boiling point? It decreases because there's less, they don't have to raise to as high of a pressure now. Now, instead of changing the surrounding pressure, now we've changed the pressure of the solution. Now, at the same temperature, by adding sugar, by adding a solute, I have lowered the vapor pressure. Is that going to make it easier or harder to boil now? Remember, in order to boil, this number has got to get up to, what is the pressure, assuming here at sea level? What is our pressure here? 760. So by adding sugar, I went from 42.2 down to 40.6. Did I get closer or further from boiling? In order to boil, it has to reach what pressure? 760. Which is closer to 760, 42 or 40? 42. So did I get closer to boiling or further from boiling? Further from boiling. It's harder to boil now. So is it going to take a higher temperature or a lower temperature? Higher. So this is leading into the next colligative property, boiling point elevation. So vapor pressure lowering, the vapor pressure got lower. Boiling point elevation, what happens to the boiling point? You guess what? Elevating means it gets higher, right? So in the last example, by adding sugar to the water, we lowered the vapor pressure. If the vapor pressure got lower, then it got further away from boiling. So we're going to have to increase the temperature even more to get it up to 760 so that it can boil. So our equation for boiling point elevation, the change in TB, or the change in boiling point, is equal to KB, which is a constant. So this is the boiling point constant here, or the molar boiling point elevation constant, times little m. What did little m stand for? Molality, good. That's the concentration unit molality. Well, not molarity, molality. Yeah. This is equation 13.6 on page 579. So by adding sugar to water, water is now going to boil, not at 100 degrees Celsius, but at some temperature higher than 100 degrees Celsius. So it increases the boiling point. And we're going to calculate just how much it increases the boiling point. So here on the same page, 759, we have a table of the normal boiling points versus the boiling point constants, and then we also have freezing point and freezing point constants we're going to use in a minute for some common solvents, water there at the top. So normal boiling point of water is 100. It has a boiling point constant of 0.52 degrees Celsius per molal, normal freezing point of 0 degrees Celsius, and a freezing point constant of 1.86 degrees Celsius per molal. Now, why is it important to know what your starting boiling point is? Because this equation does not give you your new boiling point. It gives you, what's that triangle? Change. It gives you the change. So when you plug things in this equation, you're going to get how much it changes by. You're going to still need to compare that to what your initial boiling point was and know whether or not you're going to add it, elevate it, or subtract it, decrease it. So here we have an equation, the boiling point of a 1 molal aqueous solution of some non-volatile non-electrolyte. Doesn't matter what it is. Could be glucose, could be sucrose, could be, I don't know, glycerol. It could be something. Just as long as it's something that's not going to vaporize itself and it's not an electrolyte. We'll talk a little bit about what special things electrolytes like salt does. We're just going to find the new boiling point by taking that Kb, which for water is 0.52 degrees Celsius per molal, and multiply it by our molality, and that gives us how much we change. Now to find what the new boiling point is, because it's boiling point elevation, we're going to add that change to your original boiling point. So original boiling point of water is 100 degrees Celsius. Add how much it changed, and here's our new boiling point, 100.5 degrees Celsius. So this is not going to be a drastic change, not unless you greatly, greatly increase the concentration. So moderate concentrations are not going to have a drastic change. So there's all sorts of reasons you may have heard for the whole adding salt to the water before you boil the pasta. Some of them are perfectly valid, makes the pasta taste better, sure. But one of the things I hear people say is, well, it makes the water boil hotter. Sure, it does by a small, small amount, because the concentration of salt in that water is going to be a very small amount, unless you're adding like 3 cupfuls of salt, in which case the pasta will probably end up inedible. You're not going to get a concentration high enough to raise that boiling point by a large amount. So here is showing you, this is phase diagram just like we had before, but we're looking at now what the vapor pressure is compared to the temperature as you increase it. So solid, liquid, and vapor, here's our normal liquid to vapor point, or from, liquid to vapor point. Here's our boiling liquid to vapor. As we are going to increase that line there, that comes from adding in some sort of solute. So what we end up with actually is a new line that has a higher boiling point. The difference between these two lines is your delta T, your change in temperature boiling point. On the other end of this, between liquid and solid, that's your freezing point or melting point, going between solid and liquid. This, instead of increasing, is actually going to decrease. So this TF here is going to be getting smaller. So boiling point elevation, freezing point depression. The freezing point goes down. Classic example of this is salt on the roads. So here in North Carolina, it likes to get down to like 20 degrees Celsius when the roads are nice and wet. Isn't that nice? Because it likes to rain late in the afternoon, and then overnight it freezes, and we get black ice. So to avoid that slippery surface, Department of Transportation will put salt on the roads. What that salt does is when the rain or freezing rain hits it, is that salt dissolves into the water and lowers the freezing point. Now, instead of the water freezing at 0 degrees Celsius, it freezes at some lower temperature, hopefully a lot lower than it's actually going to get here. So that's why here in the South, where we get below freezing, but not, 450 degrees below freezing, we do like to salt the roads. They don't bother salting the roads up in Canada. Why? It's still going to freeze. We're not this line didn't vanish, it just went lower. It just lowered the freezing point. But if it's negative, whatever the temperatures are going to be up there, I think I saw something in Anchorage, Alaska, that it was negative 50 or something degrees Fahrenheit. Yeah, it doesn't matter how much salt you put on those roads, they're still going to freeze. The freezing point is still there, it's just lower. Yeah. Well, the advantage there is that, for one thing, they know how to drive on snow. Yeah, they've got chains on the tires. The other good thing is here in North Carolina, the reason why the roads get so treacherous when we just have a 1/4 inch is we don't really get a 1/4 inch of snow. We get a 1/4 inch of ice. And even when it is snow, the roads are usually just warm enough to melt that snow and turn it back into ice. Up north, where the roads have been freezing cold for weeks on end, when it snows, it's just powder on top of the surface. That's not nearly as slippery as ice. So that's why down here in North Carolina, if there's a 1/4 inch of snow, we cancel everything. Whereas up in Chicago, it's only 2 feet of snow. Let's still have school.
In Alaska, I used to go to school in my snowsuit. You live in Alaska? I was born in Alaska. So we literally had to go in our snowsuits. We're like hobbling in.
My mom grew up in Illinois, and she grew up in a time when girls were not allowed to wear pants to school, so they'd have to wear skirts in the snow, walking in Illinois snow. Yeah, yeah. She said that their knees would all be like frozen by the time we got to school. All right. So freezing point depression is going to look like the exact same equation. The change in freezing point is going to be equal to a constant times the molality. But now it is Kf, or the freezing point constant. So the constants are not the same. And we go back to this table to see what they are. For boiling point for water, it's 0.52. For freezing point for water, it's 1.86, which means there is a greater effect on the freezing point compared to the boiling point. Now, it would either be water, or if I gave you a different solvent, I would go ahead and give you these numbers in the problem. But it's probably going to be water. There. But the units are the same. All right, let's use this. So car engines. Cooling and heating systems of car engines are pipes usually filled with what? Antifreeze mixed in what? Water, right? So why do we put antifreeze in there? You may not bother to put it in your car if you're down in Florida, but here in North Carolina, we do have to have some antifreeze. Way up in Canada, you're going to need a whole lot more antifreeze. So it depends on what the expected temperature is going to be in the winter in wherever you are living is going to determine how much antifreeze you put in there. So let's calculate this out. Ethylene glycol is a common automobile antifreeze. It is water soluble and fairly non-volatile. It has a boiling point of about 196 degrees Celsius. Why would you not want to put something in there that's going to cause it to boil? Do you want the water in the pipes of your car to boil? No, that's bad too. We don't want that either. We don't want them freezing over, but we also don't want them boiling. So we want to calculate what is the freezing point and the boiling point of a solution containing 685 grams of ethylene glycol in 2,075 grams of water, given that the molar mass of ethylene glycol is 62.07 grams per mole, and then the Kf and Kb's for water straight out of that table, 1.86 and 0.52 degrees Celsius per mole. Okay. So back to what our equations were. Delta T boiling was Kb times molal, whereas delta T freezing was Kf times molal. So we have Kb and Kf here. Now we need to know what M, the molal, is. So molality, again, is our moles of solute divided by what? Molarity is liters of solution. Kilograms of solution, solvent, good. Kilograms of solvent. All right, so we're given the mass of the solvent here. We have 2,075 grams of water, which is how many kilograms? 2,075 is 5. Okay, so now we have our kilograms of solvent. We got that check. So now we just need what? Moles of solute. What's our solute? For solvents, water, what's our solute? Ethylene glycol. So that's our solute. So let's take those 685 grams and convert them to moles. How do you convert to moles? Divide by molar mass. Molar mass, we are going ahead and given 62.07. Nope, but I will give you what the formula is, and you can take this formula and determine what that molar mass is fairly easily.
You said you're giving us the molality formula?
No, this part right here that was going ahead and given us in the setup, yeah, that wouldn't be given for you on the test. You'd have to calculate the molar mass yourself.
It's so hard.
You're just adding. Wait till we get to equilibrium and we have to do the quadratic formula. So how many moles of ethylene glycol do we have? Good, 11.04. So plug that into our molality equation. 11.04 moles divided by our 2.075 kilograms. And we get molality of 5.3. Yeah, 5.32. So now we can plug that into our equations for boiling point elevation and freezing point depression. So KB, our boiling point elevation, is 0.52 degrees Celsius per molal. Let me just put that on a separate sheet of paper. Keep getting a little messy here. Times molal. So molality cancels. We're just left with degrees Celsius. So by how many degrees Celsius did our boiling point change? Good, 2.8. Which means what is our new boiling point of that water? What was the original boiling point of water? 100. So we started at 100 degrees. Are we going to add 2.8 or subtract 2.8? Add. The boiling point is elevating, it's going up, so we're going to add that 2.8.
How come for these tests you have to change your test?
Because the length of a Kelvin and the length of a Celsius are the same. You could have changed it to Kelvin, but it won't change your final answer. If it was in Fahrenheit, you would definitely have to change it. But Celsius, and because you're just adding, it's not going to make a difference. Not yet. Like I said, the quadratic is coming. Sorry, I got that switched. 8.2, 2.8. There is your new boiling point. Now, freezing point done exactly the same way, except we're going to use KF, which KF for water is 1.86.
So you can just say molality.
Yep, but the molality is the same. So how much did the freezing point change by? 9.9? Yep. We've got, they rounded 9.89. So now let's find what is our new freezing point. What was the initial freezing point of water? 0. Are we going to add or subtract that 9.9? Subtract. Good. Freezing point depression. So what is our new freezing point? Good. 9.9 degrees Celsius. It's our new freezing point. So here in North Carolina, do we get below negative 9.9 degrees Celsius? Not often. Remember, this is in Celsius, not Fahrenheit. My first car was a used car, and the person I bought it from had used to live in Alaska. And so it had the plug that I could plug it in at night, the little heater on the engine that would keep the engine from freezing over. Not that I needed it, because I was here in North Carolina, but it was an option. All right, so how do we feel about freezing point, boiling point? Can we do this on lab tomorrow? Yes? No? All right, we got a couple more minutes. Let's talk briefly about osmotic pressure. All right, osmotic pressure. So what is osmosis? Something like that. Water passing through a semi-permeable membrane, right? So if you ever taken a biology class, you've used like that dialysis tubing, right? And water passes through the dialysis tubing because there has a semi-permeable membrane, meaning it has very small holes that allow small molecules like water to pass through. So osmosis is how a lot of our biological processes, such as how our veins of our bloodstream allow nutrients to pass through, or the cell walls. In some cases, the cell walls of our cells have water passing in and out. So that's osmosis. Now, as far as what direction it goes, water is going to pass through that semi-permeable membrane from an area of low concentration to an area of high concentration. So it's going to run in a direction that is going to dilute the higher concentrated side of it. So, for example, here we're going to show a colored solution to show you the high concentration versus low concentration here. So here I have two chambers. This one is low concentration. This one is high concentration. And in between this area here is a semi-permeable membrane. So which direction is the water more likely going to go? From towards here. It's going to go in that direction. So the water is going to go in that direction because what it's trying to do is lower the concentration on the high concentration side. Yeah. Yeah. No, the concentration of, in this case, is whatever these purple particles are. It's going to try and dilute the other side. So it's going to go in that direction. So that's osmosis through that semi-permeable membrane. So osmotic pressure, then, is going to be how much pressure is required to stop osmosis. Because in some cases, we want osmosis to stop. We don't want to have the exact same concentration on the inside of our cells as we have on the outside of our cells. Because every time we drink a gallon of water or go for a jog and sweat a little bit, our concentration in our bloodstream changes, and we don't want the concentration of water in our cells, in our blood cells, to drastically increase and decrease, increase and decrease. So we're going to want to have some sort of pressure across that membrane that's going to stop osmosis, and that is osmotic pressure. So the symbol for osmotic pressure is an uppercase pi. So osmotic pressure is proportional to uppercase M. What is uppercase M? Molarity. Good. Little m is molality. Molarity is the uppercase M. So here's our equation. The osmotic pressure, pi, is equal to the molarity times RT. What is R? Chapter 10. Gas constant. Good. R is the gas constant, 0.08206 liter atmospheres per mole Kelvin. And then what is T? Uppercase T. Temperature. Now, if we've got the gas law constant, what unit do you think that temperature's got to be in? Kelvin. Now we've got to have the temperature in Kelvin. Okay. That's because R has the units of liter atmospheres per Kelvin mole. There's our Kelvin. Yeah. So T is the absolute temperature in units of Kelvin. Hello. Yep. Just real quick term, and then we'll break for the day. Isotonic. What does the prefix iso mean? Same. So isotonic means the same osmotic pressure. So back to the example of somebody's dehydrated in a hospital, you give them an IV solution. Why don't you give it to them in pure water? If you give them pure water does not have the same osmotic pressure as your bloodstream, and that will cause your cells to rupture. So you have to give the patient saline solution that is isotonic, or the same osmotic pressure as their bloodstream. Otherwise, their cells will rupture. If you give somebody an IV solution of pure blood, they will die, or pure water, they will die, because it will cause the pressure will cause the pressure of osmosis will cause water to flood into their cells.
And they'll go like this.
Their cells will and think of a cell as a balloon. If you suddenly have water flooding into the balloon at very high pressure, what happens to the cell?
Like hypotonic and all that. Okay.
Yeah. Yeah.
I know that.
Yeah, you know that. Yeah, hypotonic, hypertonic, isotonic. All right, so next time we'll talk about electrolyte solutions, but tomorrow we'll have lab.